which is vector fields. So we've seen some of it a little bit, just in the form of an introduction. So now we're taking it to just spend more time doing this. First, let me start with an overview of the functions, which is what we have been studying. Okay. Okay, you've seen this already. Okay, so a little diagram of functions. Okay, can you see it? It's either too large or too small. There is no other. It's either this or that. Okay. So all right. So let me stretch it out. Okay. So so a diagram. It is like a spreadsheet in a way, or a table. Okay. So I have domain. The dimension of the domain horizontally, or domain, if you like. We can certainly change some of the names to things that might be more familiar. This one. Or less familiar. So the space of inputs on the x-axis and space of outputs on the y-axis. Okay, and then, but we're talking about dimensions. And so, as you can see, we have here the calculus 1 situation here at the very. Okay, what happened? Okay, I see. Okay. So calculus 1 in the bottom left of the table is the calculus 1. This. Okay, and okay, maybe I'll be able to draw on this better. Okay, so, okay, calculus 1. Calculus 1, and now we have done in the beginning, we did parametric curves. So these are the parametric curves. In a way, you can if you like, you can include the numerical functions as parametric curves. Okay, so they vary in dimension. So if your output space is supposed to be a vector space, but it's one-dimensional, so you end up with calculus 1 in numerical functions. Okay, so we didn't go 4 in the vertical direction, so then you go 4 and so on. Because if you get the first two, you pretty much have a good idea of what's going on with the rest of them. Okay, and then we did more recently the function of several variables. They are both horizontally here. Once again, we didn't go far beyond dimension 3 to 4. And once again, if you get the idea of partial derivatives, integration, multiple integrals, as well as Fubini theorem, you have pretty much a good idea of what is going on, except the difference here, we only did, didn't do a lot of other than partial differentiation and multiple integration, but we didn't really do differentiation as to the degree that is required in the way we did it with parametric curves. So that is actually what I want to look at right now is differentiation. So if I pick, for differentiation. Okay, let me take this. So suppose I put an arrow here that stands for differentiation, so I can find. Okay. So let's see differentiation in this table. What happens? So I start with calculus 1. It's one little cell, and differentiation goes like this. So the derivative of numerical function is just another numerical function. Okay. So when we differentiate functions, we do not leave the confines of this setting. What about the parametric curve dimension 2? This one. What is the derivative of parametric curve of dimension 2?
Is that the parametric curve?
Yes. So dimension 2. So same story. Same story. When you differentiate, you get the exact same function. So the input was a number, output was the same two-dimensional vector. Its derivative has the same property. Think in terms of location versus velocity versus acceleration. They have the same vectors as outputs. So same story here. Okay. And then and on. So every parameter curves, when you differentiate, you stay there. Now, this is where things start to become complicated. It is a function of several variables. So if you remember, what do we call the derivative of a function of two variables?
The gradient.
The gradient. Okay. And what kind of function is?
Function of two variables.
Yeah, and the output. So for each location on this plane, you're going to have you differentiate separately, and there is an output for each of them. And what the gradient at a point is what? It's made of two partial derivatives. Remember, together they form what?
Point.
No. They actually a vector. A vector is better way to think about it. So we can still think about the domain being points on the plane, but the outputs are vectors, and so for each point there is a vector, and that's where we are then. This is differentiation. Okay, so we leave the confines of functions of two variables and end up with plane vector fields, or vector fields on the plane. So when you remember those little arrows are the gradients, well, hypothetically, the gradients, and they point at the direction of the fastest growth of the function that might be this one. Okay, so that certainly already complicates things, and now if we have to study these. If we want to understand the functions of several variables, we have to understand their derivatives. And their derivatives are vector fields, and that's why we had to wait until now in order to we did integration first, and now we're doing a series of differentiation beyond just partial derivatives. Well, since we have this table here, derivatives of functions of three variables. So same logic applies. So each point will have the gradient at that point. Okay, so made of partial derivatives, how many?
3.
3. So then what do we get?
Would it be a vector field in 3 dimensions?
In 3-dimensional, and that's right. So then the input is 3-dimensional, and the output is 3-dimensional. So we actually would have to go. Let me try to make it clear. The table here, like this. So this is referring to this table, to this cell on the right. So we're gonna end up over here. Okay. So 3-dimensional input, 3-dimensional output. 3 and 3. Okay, so this is 2 and 2, and this will be 3 and 3. So the differentiation really changes things a lot. But we'll start with certainly plane vector fields. They have a lot. They just capture a lot of important things about vector fields. So it will be sufficient early on. Okay, so that is what we're after. one thing to remember, this picture is arrow. These arrows are read only one way, and then therefore I want to put it in words. So the every gradient is a vector field. Well, by nature they're vector fields, but not every vector field is a gradient. That is an important distinction. With the not really specific, easy to come up with an analog in calculus 1 that would have a similar situation, because we are talking about derivatives and functions. Among the derivatives, what function in calculus 1, as long as all the functions are like a continuous, then every function can be integrated. And what we say here, we cannot reverse this arrow. So some of the vector fields over here, they are not gradients, and therefore that differentiation cannot be reversed. Okay, so that's a profound fact that we're going to look into later. Okay, so as you can see, what has happened is a function of two variables. We differentiated with respect to each of the two variables. Partial derivatives, by the way, if we only stuck with partial derivatives, we would still stay here, right? Because every partial derivative is simply a function of two variables again. So you would have like, I'm not sure how to make it. Well, let me try to put it this way, like this. So every function of two variables, you differentiate twice with respect to each of the two variables, and you have two more functions of two variables. But that is very unsophisticated way of looking at it. We want to combine those two derivatives, and we combine them into vector fields. Okay. So all right. So there is another relation. So the relation between the two main topics and the third vector fields is number one this. But we can also connect this to parametric curves. Do you see what the connection here? Vector field on the right, that cell, and parametric curves here. Well, think flows. So among other things, vector fields might represent flows of say, liquid on the plane, with every arrow showing you in which direction a particular particle in a particular place is going. Okay. Okay. So then, if you want to trace a particular particle, what are you going to have?
So like a given parametric curve in the plane?
No, the opposite. You start with a vector field given a location, and you want to trace a particle to find where it's going, and then it produces a parametric curve. Okay, not one, but actually every single location. Let me try to illustrate this like this. You have to follow the arrows like this. I'm trying to follow those arrows like this. Okay, that gives you a parametric curve. In fact, infinitely many parametric curves, because it will be filled with those curves. The plane will be curved, will be filled with those curves. So it's like infinitely many parametric curves will be produced by one vector field. And the name for this, if you know what I'm talking about here.
I know that, like for example, if you integrate a function in calculus 1, the plus c gives you your.
It is similar. It is similar because it is this kind of integration. It is this kind of integration because what are those arrows if not changes of those parametric curves? Okay, so it is like integration. What I was referring to is called they're called differential equations. And there's a course. Anybody registered for differential equation next semester? Okay, well it's a nice course, and that's what you're going to be doing there. So at least in part. So you start here actually with one-dimensional situation, but at some point it is a vector field, and you're supposed to trace whatever the object is doing. Most of the time, I think the best way to think about a vector field and as a velocity field. Okay, so once again, there's a velocity with direction, the magnitude at every point. That's what vector field is. And if you think about it as a vector field, a velocity field, then you know what you're looking for. You're looking for actual trace. Same situation you may have had here. It's not a direct integration, because the problem, the difficulty of differential equation is that you don't know your function that you're facing is not time dependent, but it is location dependent. If you see what I'm saying. So anti-differentiation over here is your function. You know your velocity, and you want to find location. But your velocity is already function of time. You just do anti-differentiation, right? Whether or not in what dimension you do it doesn't matter. That's still parameter curves. Here, your location depends. Your velocity depends on the location. Okay, so that is cannot be. None of the methods of calculus 1 will be applicable. So you pretty much have to start from scratch. Fortunately, there are numerical methods which I'm going to mention next. And that it's called Euler's method, and pretty much it's very simple. You follow it is an approximation, obviously. Instead of trying to think of one curve, explicit formula for the curve, some sine, cosine, whatever. What you do instead, you follow from arrow takes you to the next location, and then from that location you find the next arrow and move to the next one. Okay, so. And that is maybe, let me see if this is not too small. Maybe it is too small. Okay, it's so if you have a vector field and the way you go, you are here, then you move on along to that curve to the next one. Then at that location find the velocity at that location and move to the next one. As you can see, you will be moving in an abrupt manner rather than in a continuous manner. Well, that's what the price you pay for approximations. And then if your step is short enough, and you zoom out, then you still have something that resembles a curve. And to demonstrate that, I actually taught the course last spring. So I have a couple of demonstrations, or maybe a bunch of them. So that's an example how you can carry out solve such a differential equation. So there's a vector field which is actually hard to visualize. I'll show you next. But what's behind all this stuff is at every location on the plane there is a vector. Period. And then Euler's method. So it goes back to Euler. You move. Unfortunately, there are no arrows here, but you can see that each of these they marked with different color. It is a trajectory of that particle following those arrows. And so there are just a few here, but you can imagine if you started at many points on the plane, it will cover the whole plane with those trajectories or paths of those curves. So it's uncomplicated, but very effective. And as in fact, if you take it to the next level, then you can do physics with it, such as when instead of looking at the velocity field, more likely you're going to have like force field, which is really very different. Even though it looks the same mathematically, it's the same thing. So it's still vector attached to each point, right? So is it velocity of a particle, or is it a force that is at this point applied to the object which is located there? So two very different things. So force would be, say, it could be gravitation. We'll certainly look into that. So if you know your mass and you locate it at this point that you know, and you also know where the sun is located, then you're going to know how much you will be pulled towards the sun from that location. Okay, so we did a little bit of that already, and that creates a vector field throughout the universe. Okay, and the point I was making is that it is a very different vector field, but you're not going to be solving a differential equation, rather an ordinary differential equation of degree 1, but rather degree 2, or order 2. Okay, so in other words, you have to find from acceleration you find velocity, and from velocity then you find the location. So that's all differential equations. It's certainly an important course, even though I still encourage you to register for the, what's the name of it, vector calculus, which has a different kind of challenges, a set of challenges, and but certainly differential equation is worthwhile. Well, in fact, if they cancel vector calculus, I might end up teaching another section of differential equations. So just so you know. Okay, so vector fields. Let me have a picture that I like to show you that also illustrates vector fields in a slightly different way, but seemingly more specific. Here it is. Okay, so imagine you have put little flags in your backyard or front yard. Okay, and then they're moved by the wind. Okay, so you don't see the wind, you see the flags. And so the flags then, if you look from above, they will look very much like those arrows. Okay, and then from those flags, you can figure out what the wind is doing there. Okay, it's in fact, think about, you might have seen this elsewhere, what's called wind tunnel. They put or used to put flags on a surface of an airplane to once again see how the air goes around them. So once again, they produce the vector field and they can gather some information from that. But they would have to solve their differential equation or system rather of differential equation in some way, probable Orioles method, in order to actually create a curve to show that this is how the air goes through those flags. Okay, so and then you can see especially some special points, the singularity where there's maybe some kind of turbulence, that would be very visible if you have enough of those flags. Okay, so that was introductory. And I certainly will revisit that relation between the vector fields and parametric curves, which is basically about the velocity fields, but we also will do with force field, and primarily the application will be the work of a vector field or force field. We are moving through it and how much work we have to do in order to get through it depending on the path. Okay, okay, so next. Show this. Okay, well, just one more thing. One more demonstration. I put it in the end because it's. I actually showed you a while ago, but the problem with it is always had this. It just breaks down a little bit. Vector fields. This, I think. So just one more time. No, that's not the right one. Just show you one more time what they're made of. Maybe this one. Okay. Oh, it is thinking. It is thinking. So, so once again, to remind you what the vector field is, and it is, if we just, what we have seen a few times just recently, every function of two variables is a table of numbers. Okay. Now, vector field is two of them. That's all. That's all. So, because two numbers for each location means it's a vector. Okay. And then the challenge here it is. The challenge is to visualize it, and this is the visualization. So let me. So that's the end result. That's the end result. The data and then visualization of the vector field. This is one coordinate f sub x. That is the x coordinate of the vector field, and f sub y. There's really nothing special about just a bunch of numbers. I could put any numbers there, and they will produce a vector field. This particular one, however, it did not come from anywhere, just random, but rather these two spreadsheets, these two functional two variables there, they are gradients of. Are they gradients? Oh, maybe they are. No. This is specifically Yeah, I just picked two random numbers, two random functions, and put them here in these two spreadsheets, and together they produce the vector field you just saw. But hypothetically, I could have done, which I done before, I could have produced these two spreadsheets from as partial derivatives of some other function, and then that would be different. We'll see why not every vector field is in fact not every vector field is, in fact, a gradient. Okay, well, you can actually probably guess, well, for a second. Well, suppose a vector field looks like this, and not only it looks kind of circular, suppose it has paths, circular paths. Okay, so I say this cannot be the gradient. So this is not the vector field, the gradient of any function. Do you see why? By contradiction. So suppose this is there is a function, the gradient of which is given by these arrows. Okay, so why can it not be? Well, why it is not cannot be true? Why there's a contradiction here somewhere?
It seems like it would have something to do with the graph of the circle not being single value.
Single value?
Well, I mean, for each x, that there are, you achieve two different y values.
No. No, instead, think about what those vectors are supposed to represent. If this is the gradient, then where do those arrows point? Remember, we just a minute ago I mentioned the direction of the gradient is the direction of fastest growth. Okay, let's try to grow our function. I'm growing. Come back. Okay, so what has happened?
Made an infinite staircase.
Yeah, kind of a staircase. I have come back, and I'm supposed to end up where I started, but I have grown my function. Following those arrows, I was supposed to be growing my function, slow or fast. When I have back, I'm supposed to end up in the same place. So that's a contradiction, pretty much. Okay. We'll certainly look into that later on. At this point, let's just look at something more mundane, as in just look at some examples that you can plot by hand rather than looking at the spreadsheets. It's always a good idea to start with some simple examples. So you should be able to plot it by hand. The simple example. Well, let's start with very simple ones. Well, first of all, let's understand. And once again, it's a function. Vector field is a function of two variables with two outputs. So it's really very simple. So for example, let's vxy is equal to how about xy? That's a vector field. That's a vector field. So once again, input and output. So both of them are two-dimensional. Okay, the only thing that is kind of especially appropriate to if you want to think in terms of vector fields rather than any other interpretation. There are other interpretations of functions of two variables from 2 to 2, but these are points and these are vectors. So that way, every point xy has a vector attached to it. So our v of xy is here somewhere. Okay, so that's the general picture that we usually rely on when we speak of vector fields. Every point on the plane has a vector attached to it. Maybe not every point on the plane, because it's also always possible that the domain might be smaller than the whole plane. But generally speaking, we have a bunch of points in some region, and each of them has a vector attached to it. So in other words, it's for the most part, the goal is just to be able to visualize something that is very hard to visualize, because 2 and 2 dimension is 4. Okay, so the total number of variables right now is 4. So it's getting worse and worse as we progress. And it gets harder and harder to visualize, and this is the only way that's left as far as I can tell. So for each point, there is a vector, and you have, in one little location, you have 4 numbers hidden. Then it is still possible, when you have 3 and 3, it's still possible, except you have to imagine that this being a picture in space. And so point, a vector, like this. Okay, so once again, you have kind of 6 numbers in the same spot. Okay, so if we plot, the plotting is certainly not different from plotting of a function of one variable. It is, after all, remember, vector field is just 2 functions of 2 variables. So just worth mentioning, 2 functions of 2 variables. So say f of xy is x. In this particular case, g of xy is equal to 1. Okay, so like that. So every time it's a vector, how should I put it, location-dependent vector. Once again, that picture. Each of the vectors has 2 coordinates, and each of these 2 coordinates also a function, location-based function, and that's 2 functions. Okay, so then I could just go straight ahead and try to plot these functions. It's usually not very revealing. Because 2 very, very simple functions, and you look at those 2 functions, you cannot tell what those vectors look like. And those are vector fields that are very visual. If you want to think about either what kind of forces, how they act, or what kind of motion you have through the plane, it is the vector field is to be visualized. The best way is like this. Okay, the one in the middle. Okay, so we could just as well go and just carry out all the computations on the fly. So let me try it. So the formula is available, so I'll just go ahead and have my plane like this. Okay, and then I just marked a few points that I want to look into. Just like I would with the function of 2 variables, except with a function of 2 variables, for each of those locations, I will attach 1 single number, and now I'll attach 2. Okay, so this is especially simple. I picked this very simple function. So let me just attach numbers. So 0, 0, rather vectors 0, 0, 1, 0. As you can see, the vector is the same as the point. So 1, 0, 1, 1. 0, 1, negative 1, 1, negative 1, 0, negative 1, negative 1. I'm just computing on the fly this thing. Very simple. So this is 0, negative 1, and 1, negative 1. Okay, so what's left is just to do what the picture suggests at the top. On the right, I'll just take those arrows and plot them. So usually 0 vector is just a big dot. Okay, so 1, 1, looking like this, right? Vector 1, 1, 0, 1, like that. Negative 1, 0. That's negative 1, 1. Negative 1, 0. Negative 1, 1. Negative 1, negative 1. 0, negative 1, and 1, negative 1. Okay? So, and 1, 1, 1, 0. Okay? So, that's the sketch of vector field. I have 9 points. Beyond that, sometimes you plot more, and certainly you can find things such as MATLAB or Mathematica. They plot vector fields. Wolfram Alpha plot vector fields, so that's really not a problem. But you should do it by hand a few times just to get a feel of it. Then you extrapolate. Once you have it, that you've done it once, you can imagine what's happening to beyond these 9 points, because all the points in between, and you can imagine what's happening to those vectors. So what's happening to those vectors if we move away from the origin.
Their magnitudes are getting big.
The magnitudes are bigger, yes. So say I pick a point here at random, what would the vector look like? So it will be longer. What about the direction?
It's going to we form the vector with its origin, or if it's...
Right, yeah, so it's the same, it's a radial direction, I suppose, so the same as the direction from the origin, and the magnitude is the same. So if this is, I record what's happening between these 2 points, and that's exactly, I measure as much like this, and I put it here. Okay, and that's my vector. Okay, and then, so, and then once if you go closer to the origin, those vectors will be shorter, but once again, they still be radial. Okay, so at this point, if you want to describe it, we don't really have the same language as, we could try certainly use the language of calculus 1, increasing, decreasing behavior, so we can speak of increasing probably magnitude, as well as what's happening to the direction, but it's not as easy. So you could try to, if you want to kind of get a holistic view of this this vector field, you can try to describe it verbally as to say either it is a velocity field or it's a force field, and then to say what's happening here. So let's say it's a velocity field, then what is happening here?
Our speed is increasing as we move away from the origin.
Yeah, that's right, and it is moving away from the origin. Okay, as we move away from the origin, the objects are all moving away from it, and well, can you imagine something? What would produce such a behavior of a flow?
Dropping something into like a water,
Oh,
and then go out.
yeah, but would it go faster as it's farther away from where you drop? It would be the opposite.
Slow down.
It will slow down. So this one speeds up. Can you think of a situation when it would behave like this?
An explosion?
Well, once again, it will be slow here, and then it slows down probably. So think about the flow. Well, yeah.
If we had a sphere and we, I mean,
Not necessarily a sphere, but simply we were thinking in terms of gradient, and I would pick a paraboloid probably. So because a sphere ends, and this one probably does not end, it will go all the way. So if you have upside down paraboloid, like an elliptic paraboloid, or this is a paraboloid of rotation, then it will be flowing very, and you're looking from above. So this is a view on the paraboloid from above. Okay, so it will be, point of equilibrium will be on the top, and then it will move, these points will be moved slower, but then as you are farther away from the origin, these are, they're going faster. Okay, so that is, so what have I discovered? What's the relation between these two?
the vector field is the gradient of that.
That's right, so that's the gradient. Okay, so sometimes it's possible some of the vector fields are gradients and some are not. Okay, so let's look at the more interesting one, the one that I just mentioned, the rotational one. So let's think of a rotational vector field. So another example. So we're moving in the opposite direction. So suppose I actually want the opposite. So this is, and that's really no challenge whatsoever either. I just draw what I want, and then I just read what I see. So let me read it. So instead of going radially in all opposite directions, I'll go carefully like this, in the opposite direction. Let's go in this direction. Okay. And, well, the picture always trips me out. Nothing I can do about it. Okay, so, well, let's go wider, just like we did over there. So this is 2. And then we'll just be reading. I mean, reading one by one certainly does not give you the whole story, but so you can see the coordinates, right? So this is 0, 1, 2, 1, 2, 1. Okay. Okay. So so you can certainly mark what they are. For example, this is 0, 0, 0, and this one is 0, 1, right? And this is 1, 0. Okay. So so looking at just these two, 0, 1, and 1, 0. Do you see a pattern here? So f of b of, let me write it this way, b of 1, 0 is 0, 1, and b of 0, 1 is 1, 0. I'm sorry, this is negative 1, negative 1, 0. Yeah, negative 1, 1. Okay? So you see a pattern of how we can try to implement this? Well, you see, so once again, 1, 0 goes to 0, 1. 0, 1 goes to negative 1, 0. We flip x and y and change the sign. Okay, so, I mean, I'm not sure how easy it is to guess, but that's worthwhile. So we just I write v of xy equal to negative yx. So 0, 0 is still the same, and as you can see, I certainly wasn't going to get these two. And indeed, that gives me a rotational vector field with, once again, faster rotation. And once again, try to think of anything similar to this. What kind of motion would be? Can a motion like this be produced by gravity on the surface? And the answer is probably not, even though we don't see enough stuff here. But probably not, because once again, if it did, then we would have a rotational motion that coming back to the same location while it's supposed to grow. Okay, it is in fact uncomplicated. Since we're doing this, let's show that this cannot be the gradient. We have all the tools available, so we could just as well run through this example. So rotation, hypothetically, then, so the gravity would not produce this effect, but what would, well, so it's like you need some kind of engine there in order to produce this motion, or you think of this as a force field. Then it is actually not unusual. What is it? What kind of force field is this? So this actually looks a little bit like gravity, even though in the opposite direction. But this one, what is it? Rotation. Well, anyway. So let's try. Let's suppose v is the gradient of some z equal f of xy. Okay. So that's uncomplicated. So the gradient of f is naturally d of dx, d of dy. Okay, these two functions, and it's supposed to be equal to negative yx. Okay, all right. So then what we end up with here is two equations, two differential equations, sort of. D of dx. We're looking for f. Try to find it. D of dx is equal to negative y. And d of dy is equal to x. Okay? So what do? Looking for a function of two variables, the partial derivative of which with respect to x is negative y. Can you think of, well, what do?
We just integrate by parts?
Not
Not by parts?
Not by parts, really, but one by one, coordinate by coordinate. So f of xy is then well, it is really seriously differentiation with respect to x. Seriously, very actually straightforward if you think about it. Differentiation with respect to x. Let's integrate with respect to x, right? So that's supposed to do the job, right? So negative y dx. That's all, right? So okay. So what do we get?
Negative xy.
Negative xy and plus c and. That came up last week. We are doing anti-differentiation with respect to x, which means
Plus, we're going to get a separate c for each.
we will, yes, but it's not. That's not the problem.
Plus cy.
C of y, because x is, if y is not variable, it's fixed, which means that c could be dependent on y, and its derivative with respect to x will still be 0, right? Okay, so that's what makes it interesting. So, and then we're doing the same equation, same formula, but now we integrate x with respect to y, and what do we get? Look at that, we get xy. And we have the second constant, let's say k of x. So once again, if you differentiate, you can verify it if you take this function, differentiate with respect to y, naturally xy will turn into x, but k of x will turn into 0 because x does not depend on y. Okay, so then, as you can see, that's the weird place we are, is that these two things have to be equal to each other because it's the same function. So we have f of xy equal to, on one hand, negative xy plus c of y, and on the other hand, xy plus k of x. Okay? So, any thoughts? So we need to find, we're looking for f, so we need to find these two functions, c of y and k of x. So, any ideas? No? Well, let me move stuff around. C of y minus k of x is equal to twice xy. So any thoughts, any observations? I mean, it is one equation with two unknown functions, two variables. So it certainly doesn't seem familiar, and you didn't have to deal with that elsewhere. But you just kind of shake it to see what's happening, and I'll plug in x equals 0. So what do I get? I have c of y minus k of 0 is equal to 0. Okay, now if I plug in y equals 0, I have c of 0 plus minus k of x is equal to 0 as well. So even the first equation, if I look at it, what can I say about the function c of 0 or c of y? C of y is k of 0. So what does it tell you? K of 0 is a number, right? So it does not depend on y. In other words, it's constant. It's a constant. And the same for we discover about k and the what's the conclusion? If both c and k are constant, so if this is gone, what do we discover from this equation? So c is a constant, k is a constant. What do we have?
They're equal to each other?
Maybe they might be, but actually the bigger problem is that over here, if this does not depend on y, this does not depend on x, then the left-hand side does not depend on x and y, while the right-hand side does depend on x and y. So, what's the punchline? Punchline? Okay, we'll do the punchline next time.